F322 June 2012. It's May in fact, but June 2012. Question 2. What I'm going to do here is just have a quick run through this question because it's got a mechanism in there which looks pretty scary, and just talk through some of this. So epoxy ethane C2H4O is shown here. It's used to make ethane 1,2-diol and some polymers, and it shows you the structure there. Be thinking from now what that structure of ethane 1,2-diol will be, because that's going to be useful later on. They do give you it, the structure of it, further down the question, but if you can work it out for yourself now, that's even better. So the first question is to write an equation for the reaction of the formation of epoxy ethane from ethene. So here we've got, and this fortunately pre-filled in so you don't get my bad handwriting. You've got C2H4, which is your ethene, plus oxygen gives 2 of my epoxy ethane. So here all you've done is you've broken the double bond there, and you've bonded that oxygen. Remember, oxygen needs 2 bonds, and so it's sharing 1 electron with that first carbon, 1 electron with that second carbon. Obviously in this equation you could have got rid of those 2's and put a half O2, that's no problem either. Then part 2, when burnt in excess oxygen, ethene completely combusts. So the equation you're going to write now is actually a definition. What's the definition for it? You're going to be writing an enthalpy of combustion equation, aren't you? Where ethene completely combusts in oxygen to form carbon dioxide and water. Do that by balancing first the C2, so 2 carbon dioxides, then balance for the water, so you've got H4 here, so 2 H2O there, then count up your oxygens. So here I've got 4, 5, 6 oxygens on this side, and so 3 O2 to balance it. Then you've got a huge mechanism to have a look at. Yeah, and I apologise for the quality of this background here, but it's still fairly clear. So epoxy ethane reacts with water in the presence of acid catalyst to form ethane 1,2-diol. The mechanism is shown below. So here's the overall equation. You're adding water to epoxy ethane and you're getting this diol, ethane 1,2-diol. So it's got 2 OH groups. So just looking at that equation, I'm going to have to get rid of one of these oxygen bonds. I'm going to put an OH on it, and I've got to get another OH from somewhere. So here's the mechanism, here's how it's looking. We start off, we've got, notice here, our acid catalyst, electrons moving to the acid catalyst, so a bond's going to form between the O and the H+, which is going to give us our first OH. As it does that, this bond breaks, so I do get my first OH there, so that's carbon-carbon, there's a hydrogen there, and that is a carbocation. Let me just fill that in because that's not particularly clear, is it? So here we have a plus of a carbocation because that bond has broken, so it's only got 3 bonds, so it has a positive charge. Then you've got water with its lone pair coming on to form a bond here, and this is good because we want to get an OH. What's going to happen then is one of these H bonds is going to break. Just further down, let's see if we can flip it onto the screen. Further down here, so we've got this H bond breaking, and we get our final product and an H+. Now over the page, the questions that are going to be asked are first of all, at step 2, what kind of bond fission is occurring? So here, or in fact, the first one they ask, I think, is what does a curly arrow represent? Here we have a curly arrow representing the movement of a pair of electrons. So the pair of electrons which are in that covalent bond, one from the carbon, one from the oxygen shared, are both moving to the oxygen, so that shows the movement of a pair of electrons. The type of bond fission then is heterolytic fission, because it is both electrons moving to the O and the carbon not getting any, so heterolytic fission there, which leaves that carbon then with an OH bond nicely, and this one with no electrons, so plus, so it's lost an electron, so it's become a positive. That electron has gone to the O. Then another question it's going to ask, so we've had what's a curly arrow, what kind of bond fission. It asks in step 3, how do you know that water is acting as a nucleophile? And we've got here that water's shown its lone pair there, which is being donated to the carbocation, that C plus there. So it's acting as a nucleophile because it is donating a pair of electrons. It's important that it's a pair of electrons. Remember the curly arrow showing the movement of a pair of electrons. So it's acting as a nucleophile because it's donating a pair of electrons to the carbon. Then the final question that we'll get over the page, while we're still here looking at this mechanism, is how do you know this H plus? It's told you this H plus is a catalyst. How do you know it's acting as a catalyst? Well, here in the very first step, H plus is being used up. I'm putting it onto my molecule. And then we come round to the final step, we found that we've ended up with an H plus again. So my H plus has been regenerated, it's not been used up. So it is acting as a catalyst. Think of another example of a catalyst like that. Consider radical substitution for a minute. You've got that chlorine radical, which reacts in your first propagation step and then is reproduced in your second. Again, an example of the regeneration of a catalyst, so it's not used up in the reaction. So those are the questions that are going to be answered over the page. Before I go to look at that, it's going to ask you over the page also, instead of using water in this reaction, it wants you to produce a product if you used CH3OH instead. So if you did the same reaction with epoxy ethane, but instead of using water, you used ethanol, sorry, not ethanol, methanol, what would your product look like? I'm not going over to these questions yet because it's easier to have a look at it on the actual mechanism itself. So if I used methanol instead, what would be the product that I formed here? Rather than ethane 1,2-diol, what would my product be if I used methanol? So all I would do to answer this question is come and look at my mechanism again and think, right, here instead of water I'm using ethanol. So what I'm going to write over the top of that H is CH3. It's the same thing that's going to happen because I've still got that OH group with its lone pair, its H, but instead of having just one H, I've got CH3. So here again, I can overwrite CH3. So this H, notice the bond is breaking, so I'm going to lose that H. That will go, and I'm left then with COCH3. So my final product, instead of having an H then, I'll have a CH3. I've sort of overdone that because I'll still have my O. I'll have OCH3. But all I've done, notice how similar water and methanol are. Instead of having that H, I've got a CH3, and it works through in exactly the same way. So I'm just going to go over the page now and just review, if you like, all of those answers that we've been looking at. I think I've got one extra little thing to do as well. So these are the actual questions then. I'm not going to go back to the mechanism now because I've talked it through. With that, you can use your paper to flip back. So draw dipoles in the carbon and oxygen atoms displayed on this displayed formula for epoxy ethane. Well, How do I know that I've got delta pluses on the carbons and a delta minus on the oxygen? Here I come in and think about my electronegative elements, O being part of the NOF, the NOF, so it's more electronegative than the carbon, and so it has the tendency to draw those electrons towards itself. So I have a delta minus on the oxygen and delta pluses on the carbon. Then I said that you'll be asked about a curly arrow, so movement of a pair of electrons. Key thing there being the pair of electrons it must be. Then I said that it would ask you about bond fission. Here it's heterolytic. Both electrons go to the same atom. You could also say something about bond breaks to form a positive ion and a lone pair on the oxygen atom, but I think the easiest thing to say, which does happen, is the heterolytic. Both electrons go to the same atom, and in that case it was the oxygen, because that's where the arrowhead was going, to the O. Then you've got, how can you tell water is behaving as a nucleophile? We've looked at that already, and we've said it donates a pair of electrons, or you could say it donates a lone pair of electrons. It's fine either way. Then finally we've got, with this mechanism, Y is H plus acting as a catalyst, and we've got it. You have to be quite precise here. H plus is used up in step 1 and made in step 4. It is important that you give that detail, that you do put in step 1 and step 4, so that it's clear to the examiner, you know exactly what's going on. Temptation is just to say it's used and made, and I think in this mark scheme they did actually accept that, but on other mark schemes they haven't, and they if you can show that you know specifically where these things are occurring, you're more likely to pick up the marks. Then in the final part of this question, well, it's not the final part, is it? But the final part of this section, at least I think, you've got epoxy ethane reacting with methanol, and you've got the idea here, and that's not particularly well drawn out. I preferred it over the page earlier on, but you've got your C with its OH on and your C with its O, CH3 rather than its OH. And I've got a little diagram down here showing what's happening. So the same first part of the mechanism, then you've got your CH3 instead of your H on the water, which then joins on, that H breaks off, and you're left with COCH3 on one and COH on the other. In part C, we're saying that ethane 1,2-diol is less volatile than ethanol. So here it needs to be quite precise. Ethanol is just, you've got your 1OH group. Ethane 1,2-diol has got 2. So you need to say that ethane 1,2-diol has more alcohol groups than ethanol, and it's key. You must always, if you've got 2 different molecules, you must always compare the 2. You must show a comparison between them. So it's got more alcohol groups, and so therefore it will be a stronger hydrogen bonding, or more hydrogen bonding between molecules. And it's always good to get that one in to show that you know what intermolecular forces are all about and where they're acting, because often students get confused with intermolecular forces, as you may well know. In the next part then, we're going to be asked to draw esters. So we've got ethane 1,2-diol reacting with ethanoic acid in the presence of an acid catalyst. So acid catalyst, carboxylic acid, alcohol. Key clues that it's going to be esterification, because you need a carboxylic acid and alcohol and the acid catalyst. Now it's given you as a hint the molecular formula of the compound, which may help or may not. In my opinion here, I'd be looking myself, before I try and work out what C6H10O4 is, I'd be trying to work out, well, how am I going to do this, and then check that your answer is correct using that molecular formula. So don't let the molecular formula put you off before you've used your knowledge of what could happen. So here I'm going to put up straight away what the answer is, and I'll see if I can draw out, my pen will let me, how we got that. So what you can see here is that I've got both ends of my ethane 1,2 diol converted into esters. I've got an ester link here, let's draw it for you then, an ester link here, and an ester link there, and getting one mark for that correct ester link. So even if you don't get the whole molecule correct, you get one mark for a correct ester link, and then one for the whole structure. So let's just have a quick look at how we've got that ester. We've got, I'm probably not going to have enough room here, am I? Let me zip down to the bottom of the page. So we've got our ethane 1,2 diol. Now, I'm not going to draw all my hydrogens on, you must if you're ever doing this. Then you've got, and it said in the question, excess ethanoic acid. What that indicates is that you've got enough ethanoic acid to completely react with everything. So here we've got a C double bond O, OH, CH3, and on the other side, ethanoic acid, the same thing again, double bond O, OH, and we've got our CH3. I'm not putting my hydrogens on. So in an esterification, it's also called a condensation reaction because the alcohol loses its H and the carboxylic acid loses its OH. It's going to happen twice in this case. So that is occurring. We're losing those two sets of water. Once we've lost that water, we can then go redraw. So my ethane diol still has its oxygens on. It's lost its H's. My carboxylic acid, sorry, C double bond O, CH3 is still there. We've still got C double bond O, CH3. But what then happens to form our ester is that we link the oxygen from the alcohol to the C with the C double bond O, and so we get that diester structure. And it was key here for your second mark, not only to draw one ester, but to draw the second. So zipping back up again, we have got a clearer structure there. It is important, I think I've not picked out this word, it reacts with excess ethanoic acid. That means that everything, all the alcohol groups in ethane 1,2 diol will react. There's enough ethanoic acid to react with both of them, is what it's saying when it says excess in this context. Okay, so down from there, we have ethane 1,2 diol reacts with warm acidified potassium dichromate. You have a number of different organic products formed. Now I'll come back to these organic products. I'm going to zip down to the bottom of the page again, I think. Again, so what this final question is saying, again, that you've got this diol, and you've got acidified potassium dichromate. So you've got your H plus and your chromate ions, which will give you a colour change, orange to green. And the name of the reaction, oxidation. So we're going to oxidize here. We've got two OH groups. You could first of all do distill. So potassium dichromate, distill it. What you would get, C, you'll have double bond OH. With distillation, you're going to produce your aldehyde. Then, if you do reflux, you will produce your carboxylic acid. And that, from this question, is all it wants you to do. Those are the simplest ones to do. It's a primary alcohol, because this part of the molecule is only connected to one other carbon, so it's a primary alcohol. Primary alcohol under distillation, because it wants two products that you could form. Distillation will form your aldehyde, reflux will form your carboxylic acid. So going up again to where the actual answer is here. So draw the displayed formulae. Notice that if you're not doing displayed formulae, you're not going to get marked for that. So displayed formulae, two organic products. So here I've got my carboxylic acid and my aldehyde, as I've shown you. What you could also do is not react one alcohol and just produce a carboxylic acid on one side. Accepted that. Again, you could just get an aldehyde on one side and leave the alcohol alone there. Or you could do all sorts of different things. Here we've got carboxylic acid on one side and aldehyde on the other. As long as you know that it's a primary alcohol, it's being oxidized so it can produce aldehyde or carboxylic acid, and you've got one of those functional groups in two different ways, then you get your